Welcome back. Today we're going to be looking at how we can introduce error bars into Plotly plots, specifically how to do it with scatter plots, although what we'll see with scatter plots will carry forward when we want to work with other plots like bar charts or something like that. So the first thing I want to do is sort of illustrate why we might want to use a set of error bars. So let's just start by importing some data and plotting it and seeing what happens when we don't have error bars. So as always, we're going to need to have NumPy. So we'll import NumPy as NP from plotly.subplots, import make subplots. Okay, good. So we'll go ahead and get those importing. We need the data, of course. The data we're going to look at is going to be housing data. And so in particular, the set I have is the median house price in the US by decade from 1940 to 2000, and also by state. So we have 50 states. Here they're alphabetically ordered, and we have the particular decade for which we have that information. So like the 1940s, 1950s, and so on. So we're going to go ahead and import this data and then plot it. And I think what would be interesting is to see sort of state by state, how did this change over time? So what I really want is these years as the X, and then these values for the Y for Alabama, them for Alaska, them for Arizona. So what we want is a series of arrays that are these numbers. And then also it'd be nice to have an array that is all the lists of names. So let's get those two things imported so that we can plot everything up. All right. So that would look like, let's call it state data. I guess this is the price by state, np.gen from text. And then we'll need the source for me. On my computer, I have this stored down here. So state by state housing. And if I click on the triple dots here, I can copy the path and then import that in here. So we'll go ahead and say R, put it inside a string like that. And then we want, again, if we look at the structure of this file, what we want is, if we want the prices, we basically want row by row. If you'll remember when we've used gen from text before, when we wanted columns, we had to use unpack. So what we're going to do here is just not use unpack, and that will get us back what we want. So instead, what I want to do is I don't want that first column. So I can say skip header equals 1. That gives we're not going to use those years or those decades or whatever we want to call it. We want the columns, and so remember that we generally start counting at 0. So that first column that has all the state names that we don't want, that would be column 0. And so this would be column 1, 2, 3, 4, 5, 6, and 7. So we'll go ahead and use columns 1, 2, 3, 4, 5, 6, 7. There are other ways that we could have entered those numbers, but I think that's good enough for right now for us. And then of course we always have to tell this thing like what the separation is, so what the delimiter is for our data, which in this case is the comma. All right, so running that would give us all the state data. We might as well get the years set up as well. Again, there's other ways we can get this, but I think right now the simplest way to do it is just to type it in. There's not too many of them. And 1970, 1960, 1950. You could of course try to read this using the gen from text as well. So if you like that, go ahead and do it. It might, like what this gen from text is going to return for us is a NumPy array. What we've created here is a list, and so it might be nice to turn that list into an array, and that's pretty easy to do in Python. We just say np.array and then go to the end of this and say in parentheses. And now this function basically takes the list we've given it and turns it into an array. We're not going to need it in this particular video, but we will in ones that follow this up. We'd also like to have the state names. So let's go ahead and make a variable called state names. We're going to gen from text from the same file. So let's just go ahead and copy and paste this in and change what we need to change. We still want to use or skip the header, but now the column that we want is that first column, column 0. That's the one with the state names. Our delimiter is the same, but we want it by the whole column. And remember, when we want the column, what we say is unpack equals true. And then the last thing that we need to do is we need to specify the data type. If we don't specify a data type, it can throw an error. And so we'll just say this is going to be a string, and then I don't have to worry about whether I'm going to cause an error or not. So now when I run this, what I should end up with is 3 new variables: state data, years, and state names. And let's go ahead and run that. We can look at our variables, and then you can see that I do have state names. This is an ND array, Alabama, Alaska. That would be Arizona. That's what we want. I have the state data, and you can see that basically I have an array within an array. I can verify that better if I just go ahead and press enter and run this cell that gives me that array. So what you can see is I have an array. It starts here. That's the first square bracket. And then I have another square bracket that's a new array, and that would be basically the first row of numbers. And then that array ends, and then I have another array. So I have arrays within arrays, but each one of these subarrays corresponds to the rows that we had back here. All right, that's what we wanted. So let's imagine that we were doing something naive, like we were just going to try to plot all this data together and try to show everybody what these housing prices look like. So we could call this like a single plot. I don't know, there might be something else we could call this, but let's just start with make subplots like we normally do. And then what I would like to do, if I look at the structure here, is I really want to have this array added as a trace, and then the next array added as a trace, and then the next array added as a trace. And so essentially I have a variable here, state data, that has a series of arrays. And for every one of those arrays, I would like to add it. So what we have is like, if you listen to what I said, is that for each array within this overall variable, I would like to do something with it. And so we can introduce a new coding concept known as a for loop. So let's just say here's a test equals, let's just make a list for right now. How about something that has 1, something that has the word 2, something that has 3.0 in it, and that's good enough. What I can say is for t in test, print t. And let's see what happens when I run this. You'll see that it outputs 1, 2, and then 3. And so I have different objects within this thing test, and for each thing in test, I'm going to assign it to a new variable t, and then it's going to print that t, and then it's going to go to the next one and assign it back to t. So t is what we might call like a temporary variable that we just assign each one of these in turn to. This whole thing here, where I have a for statement, it ends in a colon, I have an indentation to do something with it. We call this a control structure. In this case, it's a for loop. I indicate that I end what I want to do by unindenting. So I could say done here. And that was meant to be a string. Right, so now if I run this, you'll see that I get done at the end. If I, in the same level of indentation, printed not done yet, and ran that, you'll see that it gives me 1, not done yet, 2, not done yet. So it's doing this statement each time. So in Python, this is how we define this sort of control structure, is that we have this indentation after this colon ending statement here. All right, so we're going to use that with this array. We have the state data. So what I would like to do then is for, let's call it d in state data. Now I'm going to take a single plot and add scatter to it. All right, and that scatter then will have x equal to years and y equal to d. So I'm taking each of these d, which is each of one of these arrays, and I'm assigning it to the single plot, and then when I'm done with that, I just want to show it. We can make this look as good as we can later on if we want. So singleplot.show. And then if I hit enter, here's what we'll get. All the data plotted together. And so what has happened here is that I went through all the rows inside of state data. That was the state by state information. And I added that information. And so I ended up with something that has 50 traces, right? So if I scroll down, you'll see I have trace 49, and that's because I started at trace 0. And so here we go. I have all this data here. Now, there are things I could try to do to improve this. For instance, I could change the name of this to be the name of the state if I wanted to. But even if I did that, it becomes extremely challenging to know which one of these plots corresponds to what's listed over here. Now I do have the ability to like hover over something, and then if I had given them a name instead of just having it default to this name, that would show up. But just looking at this is very challenging. And even if they were all well separated, you'll see like here's kind of a bluish color and here's a bluish color. And which one of these bluish colors corresponds to that one, if anything? Very hard to know. In the world of sort of data visualization, this kind of mistake where we're trying to show so much data at once is called a unicorn main, because the default behavior of a program is to just keep changing the colors a bunch, and then you end up with this just like spread of colors. So this isn't really that useful for us. We'll talk about ways in a different video where we might show all of this information, but here it's not super useful. Okay, so how are we going to solve this problem? One thing that we could do is, we don't need to illustrate this for loop again right now, so I'm just going to get rid of that, is we could show instead of all of these, just what the mean value is, right? Or what the average value is. And so let's do that. We could say average by year. So we're going to make a new variable. I'm going to use a NumPy method. So I say np.mean, and then I want to take the mean of year data. Now, if I do just this, let's see what we get. So I'm going to just print out the result of running year data here. So, not year data, sorry. We need state data. That's right. Year data doesn't exist. State data. And then average by year. That's what I really want to see. There we go. You'll see that what it output was a single number. That's not really what we want. What would be nice is if we had something like this, right? So I have all of this information maybe by year, and I average it across the state, right? So if you were in Excel, you might call this equals average. Oops, yeah, it doesn't have autocomplete. Average, and then you could average from this value to that value, like this, and then you could do this for all of these rows here, and I would have the average value, and I could plot just this single row. So that's essentially what we're trying to do, but we'd like to do it within Python instead. So what's going on is that when we set average, NumPy is looking at all the numbers that exist within this state data and averaging them all. But we want just the average of each array in turn. And in NumPy, the way you refer to that is to refer to what's called an axis. So we want the average of all the individual arrays at the first level of subarray, and that's axis 1. So then we would just say axis equals 1. And this is telling NumPy to limit where the averages are. And so now you can see that we're going to have an array of averages, and these will be the arrays of each state. All right. That's still not quite what we want, right? Like we would, instead of by state, like to have it by year. So let's introduce, just to illustrate what's going on, we've averaged across the state, but we really want to average down the column, right? Year by year. So let's go ahead and do that. We need to import our data in a slightly different way. And so let's go back to this state data here. We still want all these columns. but we want it column by column instead of row by row. So it's the same thing that we had up there, but now it's just unpack equals true. And then, yeah, let's call this year data. I was one step ahead of myself before. So there we go. Now when I do this, you can see I have 1, 2, 3, 4, 5, 6, 7. Those are the 7 averages of the different years. And once I have that information, I can construct this plot. So let's call this the average plot, I guess, equals make subplots, and then average plot dot scatter x equals years and y equals average by year. And then let's just see what this looks like. So this would be average plot dot show. And now we have a single line, not this unicorn main here, that helps represent the data that we have. Now, one thing that's missing though is sort of the spread, right? Like if I look at any given year, and since I have a Plotly plot, I can zoom in, I can see there's quite a range of values. And what I'm getting is just the mean value at every given one of these like decadal years. It might be nice to still understand that there's a spread of values that are present. And one way to do that would be to not only calculate something like the average by year, but something about the spread of the data by year. And for this, I think what could be useful is to think about something like normal distributions or bell curves. And when we look at those, what we typically do is we think about something like a standard deviation in the bell curve, right? So we have a spread or a width of this bell curve, and we can describe it by the mean, which is what we used already. So we use NumPy to find the mean for every single year. And then if we had the standard deviation, we'd get a sense for like what the spread of these values are. So if we could calculate the standard deviation and then represent that, we would have an indication of the spread of values. So let's go ahead and see if we can do that. Okay, so coming back here, you might see that we had np.mean. So probably there's a way to use something like np.standard deviation. So let's call this std by year. And I'm using std because that is how we do it in NumPy. NumPy.std gives us a standard deviation. I'll say we want the year data and axis equals 1 again. And then we need to add this in somehow. Where it will go is here at add scatter. And what we want to do is show the spread along the y value. So we want to add in some indication of error along y. We're going to use error bars, and this is how you would do it in Plotly. So I say I have error for the y, and we're going to supply this a dictionary, kind of like when we have changed things about the lines of the markers before. And the type of error that we have comes from data. And then our source of the data is an array, and it's std by year. And this will be enough then to give us error bars. And so here you go. You can see that we now have these error bars indicated on our plot. All right. What else could we do? I mean, maybe you don't like what they look like these bar ends. And so one thing we could do, we could say like, let's say width, let's make it kind of silly, 50. If I do that, you'll see that changes the width at the top of the error bars. If you just want to have a bar like that, then you, without the end cap, you could do something like this. All right, there's other ways to control the appearance of the error bars, but this is something that you can work on your own. You just have to read for Plotly how you control the appearance of the error underscore y, or you can use some sort of LLM chatbot agent and ask it how you would control that. Okay. I think the only other things that maybe make sense are to fix up the axes ever so slightly. So I think I will just adjust the y-axis and be done with that. So let's say average plot dot update y-axes, And I would like to set a tick prefix equal to $, because then we'll have the price showing up here. And of course we could give this axis title, or in fact, I was going to say have US dollars, but why don't we add a tick suffix as well that is space USD. And now we actually have this all in US dollars. I think if we give this a reasonable title, so we say average plot.update layout, we could say the title is housing prices in the USA have increased over time, or we could say increased since 1940. And now it becomes very clear that this is a year that we're discussing. And if you wanted a different appearance, of course, we could set the template to something like what we've been using in this class, which is simple white. All right. I think this is, not perfect, but a reasonable looking plot of what data we have. And looking at this, it's much easier to see sort of what's been happening than it is when you look at this giant main. Now, it's not that when you look at this giant unicorn main, you can't tell that the housing prices are increasing. It's just that because there's so much information here, it's inviting you to try to figure out how to assign things. And it's like an unfocused plot where I'm trying to decipher what's going on with all these individual lines. And that's not really the point we're trying to make. We're just trying to say, hey, things have gone up over time. And so we use this average. All right. And again, you could say, I guess, the mean housing prices have increased this way. And then maybe that makes it more clear that this is a mean instead. Okay. So what would we do if we want to try to show everything instead? We'll have a different video on that using small multiples. But for right now, this is what I wanted to show, how you get errors out there. This is useful not only for the data that I showed you here, but for lots of other data that people in science or politics or social science might work with, where you want to show these kind of error bars. Okay, that's everything for this video. I'll see you in the next one.